Welcome to The Explainer. Today, we're going to crack the code behind what is, let's be honest, the most important chart in all of science. Because the periodic table isn't just a random list of elements. There's a powerful, hidden logic that tells them what to do, and we're about to figure it out.
All right, to get to the bottom of this, let's start with a little puzzle. Take two elements from the same row on the periodic table, sodium, Na, and chlorine, Cl. Now, since they're in the same neighborhood, you'd think they'd be kind of similar, right? Well, as we're about to see, that could not be further from the truth.
I mean, just look at how different these two are. Sodium is this soft, silvery metal you can cut with a butter knife. Chlorine, it's a super reactive, greenish gas. Even the compounds they make are opposites. Sodium's oxide is strongly basic, while chlorine's is strongly acidic. So what in the world is going on here?
Well, it turns out there's a hidden force, a kind of fundamental rule that's running the whole show. And once you understand it, it explains not just sodium and chlorine, but pretty much every trend you can find on the table.
Okay, so our first big clue in solving this mystery is a trend that honestly seems to make absolutely no sense at all. It's all about size.
Take a look at this. As we move from left to right across a period, like going from sodium over to chlorine, the atoms actually get smaller. You can see sodium here clocking in at 191 picometers. That's a trillionth of a meter, while chlorine is almost half that size, at just 99.
But wait a second. As you move across the table, you're adding more protons, more neutrons, more electrons. You're literally adding more stuff. Shouldn't that make the atom bigger? It feels totally backwards, but this counterintuitive idea is the key to our whole mystery.
The answer to this whole puzzle? It's this really important idea called effective nuclear charge, or what we'll just call ENC for short. This right here is the hidden rule we've been looking for.
So here's the deal. It's not about how strong the nucleus is in total, it's about how much of that positive charge, that pull from the nucleus, an electron way out on the edge, can actually feel. Because see, the rest of that charge gets blocked.
And this whole blocking effect has a name, of course. It's called electron shielding. You can think of the electrons on the inside as running interference, shielding the outer electrons from the nucleus's full attractive power.
You know what? Let's use an analogy to make this super clear. Picture this. You're at a concert. The nucleus is the band on stage, and all the electrons are the crowd.
So the band on stage, that's your positive nucleus. The inner core electrons are like the people who got there super early and are crammed right up against the stage. They have a great view. But the outer, valence electrons, yeah, they're stuck way in the back, and their view of the band is pretty much blocked by everyone in front of them. That's shielding in a nutshell.
And the math for this is actually super simple. You just take the total number of protons and subtract the number of those inner electrons that are doing the shielding. But here's the kicker. As we move across a period, the number of those shielding electrons, it stays exactly the same.
Let's see it in action. Look at nitrogen and fluorine. They're both in period 2. They each have 2 inner electrons doing the shielding. But nitrogen has 7 protons, giving it an effective charge of +5. Fluorine, though, has 9 protons, so its effective nuclear charge is a much stronger +7. You can feel that pull getting stronger and stronger as you move to the right. And hey, don't just take my word for it. This isn't just a theory. This graph shows the actual measured data. You can see the effective nuclear charge clearly zigzagging upwards as you go across each period. That pull on the outer electrons just keeps getting stronger.
And that is our answer. That stronger pull from a higher ENC literally yanks the entire electron cloud in tighter, shrinking the atom down. That's why they get smaller as you move right across the table. Our first mystery is officially solved.
Okay, so now that we have the key, this idea of effective nuclear charge, let's see what other doors it can unlock. Because it turns out this explains almost everything else.
You can basically think of it like this. ENC creates 2 completely different personalities for atoms. Over on the left side of the table, you've got your low ENC atoms. They have a weak pull, they're bigger, and it's pretty easy to snatch an electron from them. But on the right, totally different story. High ENC atoms have a strong pull. They're smaller, and they hang on to their electrons for dear life.
And this idea? It perfectly explains another huge trend called ionization energy, which is really just a fancy way of saying how much energy does it take to steal an electron from an atom.
And check this out. This graph is practically a mirror image of the ENC chart we just looked at. As the effective nuclear charge goes up,
So does the ionization energy. It makes perfect sense, right? An atom with a high ENC has a death grip on its electrons, so you need to put up a much bigger fight, use a lot more energy to pull one away.
Okay, but this isn't just, abstract physics stuff. This one single rule explains real-world chemistry, and it brings us right back to our original puzzle, why sodium oxide is basic and chlorine oxide is so acidic.
This table just lays it all out perfectly. As we march across period 3 from sodium all the way to chlorine, the ENC keeps going up. And look what happens to the character of their oxides. It goes from strongly basic to amphoteric in the middle, that means it can act like an acid or a base, all the way to strongly acidic. The trend is perfect.
So the big takeaway here is that ENC is the engine driving all of this. Low ENC leads to basic behavior, high ENC leads to acidic behavior. It is absolutely amazing how one single fundamental property of an atom dictates the large-scale chemistry that we actually see in the lab. It's just so elegant.
This quote really says it all. The periodic table isn't just some big chart you have to memorize for a test. It's this beautiful, deeply logical system, and effective nuclear charge is the master rule that puts every single thing in its place.
It really makes you think, right? It shows how understanding one core principle can suddenly reveal the logic hidden all around us. If one simple force can create all this diversity at the atomic level, what other incredible rules are out there, just hiding in plain sight, waiting for us to find the key?